I'm Dasney Joseph. We are group number 8. This is David Bush, Lina Orozco, and Eugenia de Marco. Our project is visual interpretation through color visualization of a PPR robotic platform. Basically, it stands for a drama queen. So this is a robot that actually draws, and we're gonna get into it. Abilities range from stress analysis in CAD by Lina. Research and calculation was done by me. The hardware by David. But depending on our project and the time constraints, we all collaborated to get a final project together. Our division of the problem statement is that synesthesia is a condition where you have one sense gets a stimulus and another sense interprets that stimulus into a different type of signal. A person might receive an auditory signal. It might interpret that auditory signal into a color or a shape. So several research has been done before in neurology, and a group has done a robot that actually interprets sound into mental images. For our particular purposes, we were able to take an auditory signal, translate it into a color, and from that draw a picture or a visual imagery. And based on our time constraints, this was intended for a toy. And for future applications, we might want to sample different sound frequencies and from there be able to generate a more concise drawing of a robot. So this is the meaning of our program.
So our programming was a little complex in the sense that we had to use 2 different programming languages to actually create the program. We bought the Bobot kit as well, which runs on PBasic, which is not conducive for FFT programming, which is an algorithm we use. It's fast Fourier transform. Simulated it in MATLAB. What we did was convert a song to a WAV file, which is the format that MATLAB reads. And based off of that WAV file, a matrix was created with frequency values. The frequency values were taken every millisecond. And based on this, we were able to create a matrix based which we then on the frequencies, which we then averaged into 5-second intervals, and then those averages we put into PBasic, which is what you use to program the Bobot. And as you can see, this is mainly our MATLAB code, which is the bigger one. The PBasic code was pretty simple. In our MATLAB code, what we do, we call the data from the song, x equals data, and then we set based on frequencies and sampling frequency, and then we compute a plot, and then we also compute a spectrogram, which you will see, and that will show you the different colors. Now MATLAB actually assigns 256 colors to this, which we had to reduce in size because we don't have 256 colors. Ours is a pretty simple robot, and that's what it does.
These are the results that we obtained from MATLAB. This one shows this is the first frequency sample, and over time this is a frequency plot. This is just showing you the different frequency samples that we had from our file that we uploaded, the WAV file. And then here it shows you for every time, this is all the frequencies that were gathered for that time frame. And then from that file, we're able to export these frequencies into Excel. And from Excel, we're able to average out into 4 different sections. And the highest frequency received a color of red, the second one green, blue, and purple. And that's where we are able to do our Fourier transform from MATLAB and then transport that file into a PBasic code that David will discuss mostly about in the next couple of slides.
Okay, so with that, we had to implement a final design, or we have to come up with a product. David, if you move a little bit. If you see, our robot is placed over there, and this pretty much resembles what we actually model. And the whole thing about this is it's going to be able to translate on the Y direction, X direction, and of course the N effector, which is this. Once it rotates, I'll show you. The N effector right here is going to be rotating, switching the colors back and forward. Actually, for this project, we only have 4 colors. And one of the improvement that we might primarily do, which is increase the amount of colors that is going to switch from one to the other. So that's pretty much the final design. So to come up with a final design, there's certain things that you must consider, and because there's no project without certain considerations that you need to take into account so that it will be feasible. So the design considerations, so the aspects that we consider from our design are the reliability, scalability, modulability, and transportability. Reliability in terms of this project, of our toy, since we want to market it in that industry, it won't break. Scalability is to make the prototype in any size that we actually want, which means that we could actually make it bigger than what it is, but for this project, because it is a toy, the size is appropriate. Modulability, what we want to do is that we'll be able to assemble it and disassemble it easily so that we could switch parts as they break, if they do so, primarily servos. And transportability is how easy we could transport it from one place to the next. We conducted a final element analysis. Yeah, this is not the core of the project itself, but it was necessary just to make sure, because this translates into the reliability of the project itself. So it was the final element analysis. What we did is that we just calculated pretty much the stresses that are going to be experienced on the actual structure of our design, and the maximum stresses that this will be experienced will be 11.91 psi compared to the yield strength of the material, which is wood and balsa wood. So therefore, what it tells you pretty much is that it's really not going to break, given that the material is a lot stronger than the stresses that are going to be experienced on the piece itself, for which that goes hand to hand with the displacement. The displacement is relatively small, and that will conduct into the fatigue analysis, where, as I say, it goes back to the reliability in terms of damage and life. The life, we put it to be 1 to the 10 to the 6 cycles, which means that it's extensively long, which means that if you are to purchase this toy, it will last you for a long time, so it will be a good investment. And with that, we have different components to our actual prototype, and David will explain about it.
So, we used several designing our system. As you can see, we used servos from the Bobots. We used as our drawing device, we used markers, we used plexiglass, and for this system, because it is a prototype, we used balsa wood and 2x4s. We also purchased a 2E chip, which has a little bit more memory, which we were going to need to make it run what we wanted for it to do. So this is just some of our original prototyping. As you can see, we used the plexiglass to build the end effector. And here at the end, this end effector also is plexiglass, and that's where you have your markers, which are threaded. So we thread those into this bottom. And so what happens is, as the system draws, this end effector is going to move back and forth along the beam, and this whole horizontal beam is going to move up and down along the vertical beam. Actually, it's all horizontal, but you get the picture. And as it's doing that, this plate at the bottom is going to rotate, causing a different marker to be touching the ground at one time. And so you can have different colors drawing along the x. The idea, because again this is a prototype, we can only do so much. Things we'd like to do. One thing would be to have simultaneous. Right now we can only have one marker touching the ground at a time. Again, because of budget constraints and time constraints, that's really all we could do. But we'd like to in the future use spray paint from spray brushes. So you could have different colors, different combinations. You could really have an infinite number of color combinations. We'd also like to improve the frame. The best thing to have for a toy, but we would like to use aluminum or something that would maybe be lighter and stronger, and maybe a little bit more attractive. As well as consolidating the programming. Because of the chip that we were using, we weren't able to do the fast Fourier transforms or comb filters. We weren't able to do those in the chip. We had to do those in MATLAB and then get the values from that and put it in to our chip. As well as considering other parameters. Right now we do color and speed is the idea of what we're programming in here. You could look at several other parameters of the song and maybe apply a greater pressure to change some of the other doing to kind of have a stronger correlation between the music and the visual art that you're creating.
It represents how this will work as a prototype as we stand. Are you going to talk about a little bit more about it?
Right, so like I said, you can see, but this bounces back and forth. There are sensors at each of the corners, and so the end effector knows when it reaches one of the sides, and that tells it to change direction. And so in that way, it'll bounce around and draw you a picture based on the speed and the color and what you're hearing in your song. So that concludes our presentation, and in a second, we're going to give you a demonstration of our system. Yeah, we didn't think about that.